This problem right here is one of your optional problems. The goal of the problem is to find bifurcation values of A. This is a one parameter family of linear systems. And also draw a curve in this trace determinant plane showing where the different behaviors can occur. And that curve also helps you figure out bifurcation values because it helps you think about it conceptually as well. Does anybody remember, based on either lectures or reading, what would be a good starting thing to do here? Say it louder. Find the trace and determinant. T, which will depend on the parameter A here, so you could also call it T of A. It's the trace of the matrix. Sum of the numbers in the main diagonal, that's just A plus A, 2A. And the determinant, D, which also depends on the parameter A, so you could write D of A. This is the determinant. Well, that looks like it might be complicated. Maybe it simplifies it. Okay, actually it does simplify pretty nicely. It's A times A squared, minus 1 times in parentheses A squared plus A. And yeah, that simplifies pretty nicely to A squared minus A. A squared's canceled, gives you negative A. That is the first thing to do in a problem like this, is figure out the trace and determinant. And they will depend on this parameter A. What's the next thing to do? Somebody who's watched the lectures or did the reading well enough, do you know what to do next? Setting them equal to 0 can help, yep. But I think it's probably better to make a drawing first. And what drawing am I hinting at, you think? Trace determinant plane, yeah. Make a drawing of a plane called the trace determinant plane, where your axes are labeled T and D. First thing you realize is this is not going to be a phase plane. Okay, when you start drawing the trace determinant plane, remind yourself this is not going to be a phase plane. We're not drawing a phase portrait here, at least not right away. In the book's examples, they do draw phase portraits on top of the trace determinant plane in certain spots, but the plane itself does not represent a phase plane. So what does it represent? It's kind of analogous, not completely, but kind of analogous to a bifurcation diagram. It's a diagram that helps you figure out where bifurcations will occur. That's its purpose. And there are three, they're called critical loci, L-O-C-I. It's the plural of locus. What is a locus? A locus is just a fancy old name for curve of points. So loci means curves. And there's three of them. One of them is the t-axis, so I'll make an extra boldface here. One of them, and that's where D is 0, so certainly where D is 0, you could have bifurcations. The other one is, the second one is the positive d-axis, not the negative d-axis. So setting t equals 0 could make bifurcations occur as long as D is positive. And the third one is not on the axes, it's a parabola. It looks like about like this. It's called the repeated root parabola because your eigenvalues end up being repeated roots along that parabola, your eigenvalues of the matrix. That's kind of a loose way of saying it. A more precise way of saying it is when the trace and determinant have values such that the points whose coordinates are T and D is on that parabola, then the linear system has a real eigenvalue that's a repeated root.
That parabola is the D equals T squared over 4, right?
Yep, its equation is d equals t squared over 4, which you can also write as 4d equals t squared if you like to avoid the fraction right away. Those are equivalent to each other. Why are these the critical loci? I haven't really explained that in here today. I do in the lectures. I'll try to explain it as we go to remind you. But the next thing to do is to make another graph. Anybody want to take a guess at what other graph on this graph I'm talking about that I'd like to make? Go ahead, Greg. Exactly. I really want to plot what is often called a parametric curve. Now, solutions of differential equations are parametric curves in the phase plane, where the parameter is t, time. Here, the parametric curve, the parameter is a, the parameter for the matrix. It's a one-parameter family of linear systems. Back in chapter 1, when we did bifurcations, the parameter was typically called mu. Could have been called mu here. The book chooses A. A is the parameter for the family of linear systems. It's also the parameter for the parametric curve I want to draw. How do I draw it? I'm trying to draw the points T of A, comma D of A as A changes. That has formula 2A, comma negative A. I could just plot a bunch of points, pick different values of A and plot them, and then they'd be all along a line, in fact, and then connect the dots. Though it's also important to draw an arrow on the curve, indicating the direction along the curve as A increases. You can actually just think about it as well. It's a pretty simple one here. No matter what A is here, you could say D equals, or T equals negative 2D is one thing you could say along this curve, no matter what A is, which is equivalent to D equals negative 1/2 T. And so what I'm trying to say is this parametric curve will be on the line to the origin with a slope of negative 1/2. Right, in this plane, the TD plane, D is acting like the Y, T is acting like the X. It's like Y equals negative 1/2 X, a line with a slope of negative 1/2 to the origin. So it looks like this if you don't make an arrow on it. But then you should draw an arrow indicating the direction along the curve you should move as A increases. And just think about it. As A increases, since T is 2A, T increases, so it's got to be moving to the right. Okay, so I'm drawing arrows as if that were like a straight line solution for a differential equation, but it's not. It's just showing how the trace and determinant change as A changes. T increases, D decreases. And in this trace determinant plane, the curve will go like that. And it will cross the critical loci, it looks like, at, well, actually, it looks like 3 maybe, but it's actually just 2 points. That point there and the origin right there are the 2 places where it crosses the critical loci. When you cross at the origin, you're crossing all 3 critical loci at once, effectively. I mean, the positive d-axis, you might say, doesn't include the origin, but, you know, I suppose we could include the origin. So you got 3 places where bifurcations can occur, but now we need to figure out what values of A make that happen. Well, one is easy. A is 0. We're right there at A is 0. The other one, we'll have to do some work. Evidently, since you move to the right and downwards as A increases, that other bifurcation must be negative value of A. So how should I figure out that other bifurcation value? Mm-hmm.
Both the T diagonalization step. You can figure those out and use either one, it doesn't matter. One of the equations.
Yeah. We need both T and D. And we need to figure out when they satisfy this equation. Figure out the value of A that makes that work other than A equals 0. One value will be A equals 0. So 4D equals T squared, and use the fact that T is 2A and D is negative A. If I replace D with negative A and T with 2A, I'm looking for solutions of that equation. This is 4A squared. The 4's cancel. Looks like I got negative A equals A squared. One solution of which is A equals 0. I could divide everything by A and say the other solution actually is A equals negative 1 right away. Or I could, if I want to be careful, maybe write it this way first. Factor out the A. And so the solutions of that are A equals 0, A equals negative 1. We already knew the bifurcation at 0. There's your other bifurcation value. Bifurcation points or values, it doesn't matter which word you use. I forgot what the book says, values or points. They say values. Okay. A subtle thing here. Well, okay, let's identify the types of behaviors between the bifurcation values, and there's something subtle that goes on as far as the idea of a bifurcation here. What kind of point is the origin going to be for the phase plane, for the linear system, when T and D have values that when you're below the t-axis? In other words, D is negative. When the determinant of this matrix is negative, what kind of equilibrium point will this have at the origin? Anybody know it from memory? Go ahead, Garrett. What? It is a saddle point. So down here, I'm going to put the word saddle point, and you could make a little drawing of a saddle point like the book does as well. Okay, I'll go ahead and do it. I'll draw a generic saddle point. Say something like this. That doesn't mean the actual phase plane looks exactly like that, because I drew it as if the x and y axes are the straight line solutions. They're not necessarily, right? The eigenvalues are not eigenvectors are not necessarily along the axes. They're probably not, but I'm just sort of drawing it as if they are, just to emphasize the saddle point. What happens over in these two spots when D is positive and T is negative? Then don't distinguishing between spiraling and not if we don't distinguish. Yeah, you'll have real eigenvalues when you're below and complex when you're above it. But is it a sink or a source? It's a sink, yeah. When T is negative and D is positive, the origin is going to be a sink. It could be spiral, it could be not spiral. If you're in here, it will be a spiral sink. The eigenvalues will be complex numbers with negative real part. And it's the negative real part that guarantees it'll be a sink as opposed to a source. Because from Euler's formula, well, the Euler's formula part gives you the cosines and sines. The other part, the real part, if it were, for example, -2, it get multiplied by t, and you'd have e to the -2t as part of your solution. And that would be exponential decay toward the origin as t increases. Spiral sink, when you're below the repeated root parabola, but still above the t-axis, then you have a non-spiral sink. You could just call it a real sink. But just understand that real sinks are non-spiral. You're going to have two straight line solutions in that case that are both going toward the origin. And every other solution goes toward the origin as well. Tangent to one of those straight line solutions, the one corresponding to the eigenvalue closer to 0, when I get technical about it. You can make generic pictures for these as well, a spiral sink and a non-spiral sink. I'll even make this one not be the axes. Something like that. A generic picture, not an exact picture, but the basic idea of what's going on. So it looks like for this this one parameter of linear systems, what this is implying is when A is less than -1, the T and D values are going to be over here, so the origin is going to be a real sink. As A increases through -1, the real sink transitions to being a spiral sink. A bifurcation occurs. And then as A increases through 0, that spiral sink transitions somehow in some mysterious way to being a saddle point. That sounds pretty mysterious. How could a spiral sink transition into a saddle point? We'll have to do an animation to see it. These are not bifurcations in the same sense as we usually saw again in chapter 1. Equilibrium points are not being born, so to speak. We still always have an equilibrium point at the origin. The origin is always an equilibrium point for any linear system. It's transitioning in its type. It's best it is, with some people, I call them topologists, say we only get a bifurcation at A equals 0 because you're transitioning from being a sink to a saddle point. And a topologist would say there's no bifurcation here from a real sink to a spiral sink because the topologist doesn't distinguish between non-spiral and spiral. What's a topologist? It's a mathematician who only cares about very rough ideas. That's a very loose, rough description of a topologist. So to a topologist, they just care that it's a sink. Now, whether it's spirals or not, they might care, but I'm being a bit, trying to be a bit funny here. If T is 0 and D is positive, that it does turn out to be a center, yeah. There's no exponential decay or exponential growth. They're just sort of ellipses around the origin typically for your solutions. Sometimes they're circles. Over here, you get spiral sources. Over here, you get real sources. Centers along the positive D axis. Along the repeated root parabola, when T is negative, you do get a sink still, which should make sense. And since it's a repeated root, probably you got one straight line solution. You got one eigenvector. You don't have two linearly independent eigenvectors. The matrix would not be diagonalizable, most likely. By the way, we are distinguishing between spiraling and non-spiraling. So for us, this is a bifurcation. Over here, you again have one repeated real eigenvalue, but it'd be positive. It would be a real source, but most likely you'd only have one straight line solution. Not going to bother drawing those. The most mysterious thing happens along the t-axis where D is 0. You might say it's the weirdest stuff happens there. One kind of weird behavior that can occur, and this is what's most common when you're on the t-axis when D is 0, is you have infinitely many equilibrium points all on a straight line. Why? If D is 0, if the determinant of this matrix is 0, it's not invertible. As a linear transformation, its kernel would contain more than just the 0 vector. And actually, the kernel as a linear transformation would be the same as the equilibrium points, right? Because the equilibrium points are where this equals 0. So essentially, the kernel becomes one-dimensional subspace, and all the points in the kernel, which are going to be aligned to the origin, are equilibrium points. Got infinitely many equilibrium points. What do the other solutions look like? That's the weirder part. The most degenerate case, however, can occur when you're at the origin. One degenerate case that can occur, not for this example, but for some other examples when you're at the origin, is the entire plane could be equilibrium points. When would that happen? What would your matrix be to make the entire plane be all equilibrium points? It doesn't happen for this example, but. Say it again? No, I'm talking about 2 by 2 matrix still. Go ahead. The only way every point in the plane is going to be an equilibrium point is if all the entries of your matrix are 0. It's the 0 matrix. The differential equations are dx dt is 0, dy dt is 0. Very, very simple. No change going on anywhere. Every point is an equilibrium point. Okay, that's the most degenerate case. It's also very simple, but that's, you might say, the strangest thing that can occur when both t and d are 0. Doesn't always happen when both t and d are 0. I mean, that happens here for this example when a is 0, but you do not get the 0 matrix. You get 0, 0, 1, 0. That ends up having a line of equilibrium points. So let's take the time to use Mathematica to animate this. Quickest way to do that is just to animate the stream plot. As a varies, say, from -2 to 2. Stream plot of what? Stream plot of the vector field corresponding to this matrix. So a times x. I better multiply it out to be careful. Yeah, okay. In my head, I was doing a times x plus a squared plus a y for the first component of the vector field. And then 1 times x, just x, plus a y for the second component. That's going to be the vector field that I need to put into the stream plot with curly braces. A times x plus a squared plus a times y, comma, x plus a times y. So now we're looking at the actual phase plane here, not the trace determinant plane. You can see when a is less than -2, the origin is a sink, a non-spiral sink. Remember, as a increases through -1, it's going to transition to a spiral sink. And then as a increases through 0, it's going to transition to a saddle point. Let's do it slowly here. Okay, so I hate when it does this. Okay, there we go. It's fairly slow. There's the transition, not yet, to a spiral sink. Right now, it's tough to tell the difference at the boundary. And transition to a saddle point as a increases through 0 right about now. There we go. So the weirdest behavior is when a is just less than 0, it's still a spiral sink in that case, but these spirals are becoming very skinny in the vertical direction, and they become skinny enough as a gets close enough to 0 that there, when a is -0.001, you can't tell it's a spiral sink anymore, even though it would be. At -0.01, it's a little bit more clear, but still tough to tell. It's hard to draw a super accurate graph in those cases. When A is bigger than 0, it has transitioned to a saddle point. Yeah, that's when you're going to have infinitely many equilibrium points. It looks like the y-axis probably is, yeah, the infinitely many equilibrium points. And if we think about the equations themselves, when A is 0, it would be dx dt is 0. So yeah, there's no motion in the x direction, and dy dt is x. And along the y-axis where x is 0, you'd have equilibrium points. That would be 0. The y-axis, x is 0. All points in the y-axis would be equilibrium points. If you're to the right of the y-axis, solutions increase, dy dt is positive, because x is positive. If you're to the left of the y-axis, solutions decrease, dy dt is negative, because x is negative. Dy dt equals x when A is 0. Of course, mathematics is not drawing the equilibrium points. You need to just realize they're there. Every point on the y-axis is an equilibrium point. It would be the case that solutions that are closer to the y-axis, the motion would be slower, upward or downward, than solutions that are further away, that the motion would be faster. Okay, let's relate this stuff to your other main topics to work on for homework. Thinking about mostly about diagonalization and when things are either diagonalizable or not, and also relating things to the beautiful generalization in the matrix exponential. Let's go ahead and consider the same example here. Well, let's pick a particular value of A. Why don't we pick one where it's a saddle point? Like A is positive 1. If A is positive 1, the matrix will become 1, 2, 1, 1. That's a matrix that I've often used for P, right? But here I'm using it for A. Now we're in the case where capital A, say, is 1, 2, 1, 1. I guess I did have the column switched around. I had P to be 2, 1, 1, 1. I often pick that P because it has a determinant of 1, so its inverse is simple. This one has a determinant of -1. Its inverse is still simple, but I don't need to think about its inverse. This is the case where the little a from the previous problem was positive 1. This is going to be the origin is going to be a saddle point for the corresponding linear system. dy dt equals ay. It will be a saddle point. We already know that. If I want to find a formula for the solutions, as usual, you'd want to figure out the trace determinant, figure out the eigenvalues. Does it end up being simple here? These are probably going to be irrational numbers. Oh, well, we just got to live with it. Sometimes you have to live with irrationalities. Eigenvalues are 2 plus or minus square root of 4 minus 4 times 1 times -1 over 2, quadratic formula there. 1 plus or minus square root of 8 over 2, which simplifies to 1 plus or minus square root of 2. The eigenvalues are about 2.4 and -0.4. 1 positive, 1 negative. The origin is a saddle point. I think I don't want to find the eigenvectors, though. We could have Mathematica approximate them. It'll write them in exact form if I don't use a capital N. if I do use a capital N to numerically approximate them, I can approximate them. And actually, if you use a capital N inside the eigensystem in front of just the A, I think it'll also normalize the vectors, the eigenvectors. In other words, make them approximately unit length. Another way to do that, well, okay, let me just leave it at that. So these vectors, I can draw them approximately. I could draw a quick phase plane here. So one of them is approximately 1.4 comma 1, and the other one's approximately negative 1.4 comma 1. So a quick picture of the phase plane. My straight line solutions are going to be along lines that look about like this. This line parallel to the vector whose components are approximately 1.41. This one along the parallel to the vector whose components are approximately negative 1.41. The origin will be an equilibrium point. Which one corresponds to the positive eigenvalue? Which one to the negative? Looks like this one's to the positive and the other one's to the negative. So a source in that direction and a sink in this direction, and other solutions are going to look about like this. I'm not bothering to draw the null lines in this example. Certainly to get a more accurate picture, I certainly could. But this is a pretty decent picture if I don't include the null lines. That's what it's going to look like. Where am I trying to go with this? I'm just realizing I should have picked things to make nice eigenvectors, eigenvalues and eigenvectors. Okay. So we're going to have to rely on technology here to do the calculations for us because they're not going to be nice numbers. But the principles still work, okay? The next thing to do to diagonalize is to create your P matrix. And this is going to be diagonalizable. Why? What theorem, or describe a theorem that would guarantee that the A here is diagonalizable? What facts about A would guarantee that? Just looking here would be enough. Two distinct eigenvalues, real eigenvalues is enough to say A is diagonalizable. Actually, don't talk about diagonalizability so far if the eigenvalues are complex. If the eigenvalues are complex, which would automatically mean they're distinct because they'd be complex conjugates. The matrix could be said to be diagonalizable in that case. However, the corresponding diagonal matrix would turn out to have complex number entries. And that would not be so useful. I do address this in a lecture for next week. In such situations, we actually don't try to diagonalize, but we do still try to create matrices like the P matrix to still put the system in a simpler form, do a change of variables to still have a simpler form, even though it won't be completely uncoupled, even though the matrix will not be diagonal. It'll be simpler. The principle is you put the eigenvectors in the columns P. And if I'm going to make this work precisely, I don't want approximations. I want these things involving the square root of 2. Okay, well, that just happens sometimes. So I could take, for example, this one to be the first column of the matrix. Square root of 2 plus 1 and 1. Oops, no, not plus 1. 2, square root of 2, 1. And the other one, negative square root of 2, 1. That's how you create P. You make its columns be the linearly independent eigenvectors. And this applies to bigger matrices as well. 3 by 3, 4 by 4, 5 by 5. If you've got a basis of eigenvectors, say for a 5 by 5 matrix, you've got 5 linearly independent eigenvectors. You put those eigenvectors in a matrix for P. P is not unique, just like eigenvectors are not unique. I could, for example, multiply the first column of this by 2. I could use that for P instead. It is a different P, and it does have a different P inverse, but the ultimate diagonal matrix turns out to end up being the same. I'll show it to you. I'll illustrate it. I'll go back to the original one though. How do you create the diagonal matrix of interest? You create it by doing P inverse AP. The D matrix is P inverse AP. This equation is also often written in the alternative form A equals PD P inverse. You should know both equations. I remember recall in my mind that you start with P inverse if you want to get to D. P inverse needs to be on the left of A. That's the way I remember it. Another way to remember it is if you want to get to A from D, start with P on the left. You can remember it either way. This is the way I remember it. I start with this equation, then I know I can get to this one. How do you get from here to here? I showed you already, I think. It's 2 steps. You'd want to take this equation and first multiply both sides on the left by P to get PD equals AP, because the P inverse will cancel with the P. Multiply on the left by P to get PD equals AP. And then multiply on the right by P inverse to get PD P inverse equals A. Because once again, the P and the P inverse cancel. Cancel to give you the identity matrix, which you don't bother writing down. Ultimately, that means A does equal PD P inverse. If that is confusing, write the steps down on your own. It's worthwhile to do. So what I'm saying now is if on Mathematica, if I do P inverse, which you have to type as inverse P, times A times P, I should get a diagonal matrix with the eigenvalues along the main diagonal. These numbers. In the same order as the corresponding eigenvectors. So since I put the eigenvector corresponding to the first eigenvalue in the first column, I would get 1 plus square root of 2 in the upper left. And since I put the second eigenvector corresponding to the second eigenvalue, I'll get 1 minus square root of 2 in the lower right. But it's not simple enough yet to see that. Simplify. There we go. Again, I know this is confusing. Whether you do slash, slash, or square brackets is a little confusing. You can do it either way. Slash, slash is just a way of doing an operation after the fact. I also could have done simplify to the left with square brackets in the same, it does the same thing. Sometimes I also do slash, slash matrix form at the end. It's just 2 ways of applying a Mathematica function. There we have it. And yeah, yes, if I switched P, multiply the first column by 2, I get the same answer in the end. Even though P and P inverse are different now. I multiply the second one by 3, I'll still get the same answer in the end. If I multiply both columns by some non-zero number, I'll get the same answer in the end. What's the purpose of diagonalization? You don't find it in our textbook, right? Because the textbook is focusing on the differential equations. They're just trying to get to the solutions in the phase plane as fast as possible. But we're trying to relate this to linear algebra. So we're trying to relate this to coordinate changes. The P matrix is your coordinate change matrix. And we're trying to emphasize that what P does is it creates, in a sense, skewed coordinates. The best coordinate system to use to view this phase plane is with the eigenvectors, the straight line solutions being your new axes. Effectively, if those are your new axes, your skewed axes, then the system becomes simpler. It becomes completely uncoupled. And you can solve it just by looking at it. Right? This D matrix is diagonal, so the system corresponding to this D matrix is completely uncoupled. Let's go ahead and write it down. What would it be? So the D matrix here, for our example, one plus square root of 2, 0, 0, 1 minus square root of 2. And you can double check that multiplication if you want. It's worth doing at least once. Double check and not just believe the technology. The corresponding system using, say, a new variable, call it u as a vector. And if that vector u has components little u, little v, as a system, it would be du dt equals 1 plus square root of 2 times u, and dv dt equals 1 minus square root of 2 times v. And that's a completely decoupled system. You can just look at that and see the answer. And if I have generic initial conditions, u of 0 equals u sub 0, v of 0 equals v sub 0, I can write down the solution. As two scalar equations, the solution would be u equals u0 e to the 1 plus square root of 2 times t, v equals v0 e to the 1 minus square root of 2 times t. In vector form, capital U would be u0 e to the 1 plus square root of 2 times t. For the first component, that's a square root of 2 in a parenthesis there. And the second component is v0 e to the 1 minus square root of 2 times t. Sorry, that's hard to see. That again is a square root of 2 there and a end parenthesis. That didn't get drawn very well. But this is a function of t. When u0 and v0 is fixed, it's a solution of the system. I could call it capital phi sub u0 of t, but to just use a different letter, I call it capital psi. More Greek letters. To distinguish it from capital phi, that's the reason. This has nothing to do with quantum mechanics, right? You know about psi in quantum mechanics? If you don't, you will. Modern physics. It's called the wave function, Schrödinger equation. If you've ever heard of those things, you will learn about them in modern physics, and if you take quantum mechanics. But this has nothing to do with quantum mechanics, is all I'm trying to say. It's like a joke, okay? Nothing to do with quantum mechanics. And this is also related to the matrix exponential. This vector here can be decomposed into a linear combination. The scalar u0 times the vector e to the 1 plus root 2 times t 0 plus v0 times the vector 0 for the first component and e to the 1 minus root 2 times t. But remember, a linear combination of vectors can always be thought of as a matrix multiplication, a matrix times a vector. This, by definition of matrix times a vector, is the same as this 2 by 2 matrix, diagonal matrix, times the vector u0, v0. And this is the matrix exponential of the matrix TD times the initial condition vector U sub 0. And that is the beautiful generalization that this solution can be represented in this way. And if you don't believe it, you can have Mathematica confirm it. Go ahead and keep writing. I'll go to Mathematica in about 30 seconds here. All these things are tied together. But you can't just listen to this stuff once and get it, right? You can't probably just listen to it twice and get it. You got to think about it. Work with the examples and think about it. Confirm the calculations. Why does this equal the matrix exponential? That's related to the definition of the matrix exponential as a Taylor series. And the fact that D is diagonal makes that Taylor series easy to evaluate. It's when A is not diagonal that the Taylor series is hard to evaluate, because the powers of A become more complicated in that case when A is not diagonal. But we can confirm this calculation here. Let's give this matrix a name. Let's call it D. I don't want to use a capital D in Mathematica because that's reserved for derivatives. Okay, so I want to do the matrix exponential. Matrix X of the matrix TD. Oops, not capital. There it is. This matrix is 2 by 2 matrix. And if I multiply it, it's writing that, I get that in a funny way, but just distribute the minus sign through. Suppose I could simplify. Okay, well, it does funny things sometimes. If I multiply this by the initial condition vector, U0, V0, then that matches the solution right here. But what am I trying to do with all this again? I'm trying to get back to the original system with the original matrix. With that matrix. How do you do that? Use the change of variables matrix, the P matrix, which is only in Mathematica. The P matrix again was, I'll write it down here. Square root of 2, 1 for the first column, negative square root of 2, 1 for the second column. Let's write down this by hand in a few different ways. Okay. It's probably simplest to think about initially in terms of the actual components. Well, okay, we gotta go back to thinking about coordinate vectors. Okay, but I'm not going to use the coordinate vector notation. I'm not going to write except right now. That kind of thing. But coordinate vectors are here. Okay, I'm just not going to write that. What I'm going to do is I'm going to think in terms of new variable. And I always remember that it's the old variable, which in this context I should call y, is p times the new variable, pu. pu, okay? Remember, I mentioned this like a week or two ago. It's the opposite of what you think it should be. You'd think if I'm doing a change of coordinates, I should probably write the new variable in terms of the old. But no, it works out, you want to write the old variable in terms of the new. I mean, this does give you the new variable in terms of the old as well. You could, it's equivalent to saying u is p inverse times y. Guess we're not having much work time today, but I think this is pretty important to help you understand the assignment. First page of notes again is good enough for CP. Okay. In terms of components, this is xy equals that matrix times uv. And in terms of the individual scalars themselves, you could say x is square root of 2u minus square root of 2 of v, y equals u plus v. I think if I recall correctly, we also will need the inverse transformation. P inverse, use the shortcut formula, 1 over the determinant. The determinant is going to be square root of 2 minus negative square root of 2. It's going to be 2 square root of 2. Switch around the numbers in the main diagonal, negate the numbers in the off diagonal. That's P inverse. We can multiply the 1 over 2 square root of 2 through the parentheses here and write this as this, and with the second column, the square root of 2's cancel. And if we want to rationalize the denominator there, not that you have to, but multiply the top and the bottom of these fractions by square root of 2. We'll get square root of 2 over 4 minus square root of 2 over 4. So all this is trying to say is that if you solve this system for u and v in terms of x and y, u will be square root of 2 over 4 times x plus 1/2 y. V will be negative square root of 2 over 4 times x plus 1/2 y. Maybe I should have Mathematica double check that. That does match this. And I'm confident that I rationalized the denominator okay. We'll need both, is what I'm trying to get at here. So here's one way to now relate. The goal here is we're trying to relate this completely decoupled system to the original coupled system. How? These equations are going to imply for dx dt that it's square root of 2 times du dt minus square root of 2 times dv dt. And for y, dy dt is du dt plus dv dt. Now go back to the equations for du dt and dv dt. From the completely decoupled system, this one here. Replace du dt with 1 plus root 2 u. Replace dv dt with 1 minus root 2 v. Okay, keep going. Multiply those root 2's through. This becomes root 2 plus 2u minus or maybe I should put plus negative root 2 plus 2v. And that's the same as 2 minus root 2, whatever. Now do what? Now use these equations. Yeah. Plug those in there and there. This is not an easy process. Lots of places to make mistakes, but it's worthwhile to do. Root 2 plus 2 times root 2 over 4x plus 1/2 y. I think I won't bother doing the same calculation for dy dt. And then plus negative root 2 plus 2 v is, looking here, negative root 2 over 4x plus 1/2 y. And if I've done things right and haven't made a mistake so far, this is going to simplify very nicely, and I can predict what it's going to simplify to without actually doing it yet. I predict it's going to simplify to x plus 2y. The first column of the A matrix times the vector xy, because that is supposed to be dx dt's equation. Let's see if it happens. Got a FOIL. Okay, first times first, root 2's times themselves become 2 over 4 is 1/2 x. Outside times outside is root 2 over 2y. Inside times inside is 2 root 2 over 4x, which is the same as root 2 over 2x. Last times last is plus y. Now FOIL these. I'm using parentheses, but I didn't have to. First times first, negative signs cancel. Root 2's times themselves become 2 over 4 is 1/2 x. Outside times outside is minus root 2 over 2y. That'll cancel with that one. Inside times inside is minus 2 root 2 over 4x, and that'll cancel with that one. Last times last is plus y. This does simplify to x plus 2y, like I guessed. That first column, first row times the vector xy. I won't do the details here, but this one, after you do the details, should simplify to, look at the second row, x plus y. This is directly relevant for your homework, okay? So that's one way to verify that the change of coordinates matrix P essentially converts this completely decoupled system back to the original system. It also works the reverse. Here's another way to verify it. This way is in some ways easier, though. In some ways easier, some ways conceptually more difficult, perhaps. You can do it at a vector matrix level without all the scalars. It's more abstract. I'm not going to say what the matrices are. I can write, since y is pu, I can differentiate both sides with respect to set t and say dy dt is p times du dt. P is a constant matrix. Du dt, though, is d times u, right? The diagonal matrix times u. That diagonal matrix. Based on that. But wait a minute. Since y is pu, U is P inverse Y. So I can replace U with P inverse Y. Then use the associative property and write this as P D P inverse Y. And that is AY. Because this thing here is A. That's an easier way to go, actually. But it's easy to be confused. And you also can say that e to the TA, the matrix exponential of t times a, where a is the original non-diagonal matrix, is e to the t times p d p inverse. And it turns out this takes proof, skipping steps. I do prove it in one of the lectures, that this equals p e to the t d p inverse. And that is a good thing. If we wanted to figure out the solution of the original system using the matrix exponential and the beautiful generalization, we could do it without technology. Because e to the TD is easy to find. P and P inverse are, well, the numbers are not so nice, but they can be found pretty easily, and you can do this matrix multiplication pretty easily. So this could help us solve the original system, use the beautiful generalization for the original system, write down the formula for the solution, and I think on the homework I have you do that. This is all pretty nice when A is diagonalizable. But what about if A is not diagonalizable? Evidently, this doesn't work anymore. There's no D matrix anymore. So what do you do? Well, you don't use a diagonal matrix. You use an upper triangular matrix in place of D. It becomes harder. It is still a harder problem, but it is still doable. And in a lecture next week, I'm going to watch for a lecture about Jordan canonical form. Jordan written as if it's Jordan. But everybody says Jordan when they talk about Jordan canonical form. This Jordan canonical form that I'm hinting at is a very difficult topic in general. But in the lecture, I do it in the easiest case. And you definitely can understand it in the easiest case. Okay. It's not in the book. So you're going to want to make sure you watch the lectures to help you understand the PowerPoints as well. So I know there's just so many ideas here, so many equations all over the place. Which again means you need to spend some time thinking about it and double checking calculations to help you believe things and make the mental connections to understand it. Again, you don't find the matrix exponentials in our book. There are plenty of differential equations books that have them, though, out there. But I didn't like other parts of those books, so that's why I went with our book and supplementing otherwise with this other stuff. All right.